I can see it.
All righty. So going into chapter 7, this is about tests of significance and measures of association. And so a lot of this has to do with inferential statistics and testing hypothesis. And so one of the big things to remember is that the difference between two sample means difference between two sample means is the random error. And so a test of statistical significance helps decide whether an observed relationship between an independent and variable dependent really exists in the population, or if it could have happened just by chance when the sampling was taken. And so this is going to come up to the type 1 and type 2 error. So like I just said, difference, oops, one more. So here in chapter 7, we're going to do the difference between two sample means and standard error. So this is what I just read about the test of statistical significance. It's just helping us decide whether or not there actually is a relationship between the variables. So this is a lot of the statistical significance. You know, this is where we start with the null hypothesis, or the beta naught, which is that we are believing that there is no relationship that exists in the population between these two variables. And we believe that, and we set the 95% confidence interval to make it difficult to reject it. Now, conversely, the hypothesis we're trying to prove is the alternate hypothesis. So, and this is where we always begin by assuming that random sampling error explains the result, and that we assume the null hypothesis, the beta naught, is true, and we proceed by setting a high threshold for rejecting it of 0.05 level of significance. So then this is, you know, and we get that 0.05 with the p-value when we run linear regressions, and also any type of regression, linear or logistic regression. And so the p-value is less than or equal to 0.05, then the null hypothesis can be rejected. So now we get into our two errors, and he did say that these errors are going to be on the final. So type 1 is when the researcher concludes that there is a relationship, but in fact there is none. And type 2 is when the researcher infers there is no relationship, and in fact there is. I'm not really sure how you want to try to remember that. Type 1 is that there is a relationship, is where the researcher thinks that there is when it's not. And type 2 is when the researcher says that there's not, but there actually is. Just got to kind of figure out some way for you to remember that. So in here we have, you know, this is kind of what we went over before. This is, if we have any problems like this is how I expect us to get them. X bar equals 59, standard error is 2.5. And so we have, you know, we get our upper and lower bounds of 54.1 and 63.9. We are 95% confident the true mean lies within 54.1 and 63.9. Then this is the example where someone else says, oh no, it's 66. And so here is where we use this Z statistic. And so we have hypothetical mean minus the X bar. So this 66 is what the other person is saying. And see, this is the hypothetical mu. So this is what they are saying, and it's Greek. So that's what we're thinking that the actual, like what the real world mean is. So Greek, anything Greek letters, that's the real world. And then when it's Latin letters, like the X bar, that means that it's just the sample. So we have the real world hypothetical real world mean mu of 66 minus the obtained observed mean of 59. And then we're going to divide that by the standard error. So 7 over 2.5 equals 2.8. So now we locate the value of Z using probability table or R. The interpretation is if the true population mean is 66, then we would observe a sample mean of 59 a total times of 26 times out of 10,000, and we can reject this. So like I said, for this part, this 2.8, like it says, we would normally be using R to find that out. And so I don't think we need to worry too much about that. But it is just important to be able to understand the testing the hypothetical minus the X bar divided by the standard error. And so now we get into our standard normal bell curve and the 2.5. And so this is where we're comparing two sample means. And so Obama-Thurm, men versus women, and compare the 95% confidence intervals. If the interval overlaps, we can reject the null hypothesis. So this is saying that, you know, for Obama feeling thermometer for men is statistically different than the feeling thermometer for women. So the null hypothesis would be that they are not, that they are the same. And so this is why if they do not overlap, because if they were the same, they would overlap, we can reject it. And so here we're given a female mean. And so we go through and find, and the standard, we're given the standard error. And we go through and we find the upper and lower boundaries, do the same thing for the male. We have the mean, the standard error. So the same thing, mean minus 1.96 times the standard error, get our upper and lower. And so we can tell that these do not overlap. I think that they even come and then they put it on a box plot. You can see that they're far away from each other, so that was true. And that is basically it for chapter 7. Let me see if I had any other notes to go over. Was there any questions about anything right now?
I'm good right now.
Okay.
Thank you.
All right. So, okay. So back to this is one note that I had from class. So back to this 2.8. So this number is supposed to be pretty much like if it's going to be correct, it's going to be around the 1.96. So like how we have this 1.96 to get that 5%. To fall within the 95 percentile. I don't know if you guys remember that from class, like to fall within here so that it's able to be rejected, you needed it, the number comes out to 1.96. And so this 2.8 is that same number. So since that's way bigger, we can reject it. Like I said, it's not really that big of a deal, honestly, I believe. The other thing, and we'll get to that later. All right, if there are no questions on that, we're just going to move. That one was super quick, so we'll just move straight into chapter 8 and try to get 2 of these into one video. Any questions before I start chapter 8?
I'm good. Thank you.
All right, so correlation, basically, it's known as Pearson's correlation coefficient. This is just saying that when you have a change in X, you have this certain change in Y. And that, they're shown on scatter plots through changes in the X and Y thing. And then the Pearson correlation is normally shown by lowercase r. And so a correlation is a ratio. And so it's always between -1 and 1. So here you can see 1 means perfect positively correlated. So that means for every 1 increase, in X, you're going to have, a positive increase in Y. A positive increase in X turns into a positive increase in Y. While a negative number would be with a positive increase in X, you're going to have a negative increase in Y. Or with a negative increase in X, you're going to have a positive increase in Y, depending on where you're at. But so it's the same. And then 0 means it's like a spurious relationship. There is no correlation. It just doesn't seem to, it just is either straight across no matter what the value is, or it just goes everywhere and there is no correlation. Here's an example. Also with the correlations, there's also the like strong and weak versions. We'll see some of these graphs here quickly. So positive correlation, so 0.95. So that's a really strong positive correlation because it's closer to 1. And so you can see that it goes up like that. This is a weak positive correlation. It's only at around 0.5. And so you can see there's a general trend of going up this way, but it's not as tight as that previous one. And then we have a strong negative, again, around -0.9. And then this is just a no correlation. It's almost at 0 and it's kind of just all over the place. And then there's also parabolic relationship. So this one I could see him putting on the test. He'll just show this and be like, what type of relationship is this? Or what type of correlation is this? And so it's a parabolic. And so you can tell that because it goes up and then comes back down. So then we're going to get into the bivariate regressions, which is just our simple y equals a plus bx. B, is the slope of the line. So there, we just have our standard y equals a plus b. And so when we have our linear regressions, I think these were called like hats or something like this. So this is y hat equals a hat plus b. And so with these, the hats are like examples, and kind of just show you like those are the real world, like what they were, compared to like you'll see some where the where like if you're given this value of a, then or this value of x, then your y should equal this. But because of like the difference in your error, you get a difference. So linear regression equation, the y hat is an estimate. Okay, so sorry, I was wrong. It's opposite. So these are the estimates. The y hat is the estimated mean value of the dependent variable. The a hat is the average value of the dependent variable when the independent variable is 0. B hat is the average change or slope, independent variable, unit change, and independent variable. So A is still your like y-intercept, basically. So when X is 0, then A is going to be your y-intercept. And so then the standard error B is the B hat plus or minus the standard error of the B hat, which qualifies the noise and is estimated regression slopes based on how closely the predicted values of Y and approximate of. So then here we have our errors or our residuals, which is the Y1, which this is what the actual Y value was minus what we thought the Y value was going to be. And so then I'm sure you guys remember this, where we thought, you know, it was going to be up here, but it actually ended up being down here. And so those are residuals. Any questions on residuals before we go forward? All right.
Yeah, just to make sure, the residuals, the observed minus the predicted, right?
Correct.
Okay, thanks.
So, and so here you can see, like, basically your Y hat is, so if you plug 5 into this equation for X, you have 10 plus 1, so your Y hat would be 11. That was your predicted. But your actual, your Y, ended up being 10. So you have, so it's the actual minus the predicted. So I'm not sure if I said that the wrong way before, but it's the actual minus the predicted. So 10 is what you actually had, and then you subtract what the predicted was to give you -1. So same thing here, 2 times 2 is 4 plus 5. It was actually 6. 6 minus 5 is 1. And then 3, 6, this was 7, 7, and equals 0. So if this was 1, that's 2, that's 3. And then you actually had 5, so 5 minus 3 is 2. So any questions of how to get those errors from the residuals?
Nope.
All right. And so this right here is another thing that he said was going to be on the exam, is that errors are the difference between the predicted and the observed. So I'm not sure if it's just going to be, you know, errors are A, B, C, or D, and you have to find the difference between the predicted and the observed, or it could be, you know, you know, just like this slide right here, where you need to fill out E. But so that is a thing that is going to be on the final. So now we just get into the p-values of 0.05 and the stars system, 1 star, 2 star, 3 stars. When you go into your hypothesis test. And so this, just go through my notes and see if there was anything. So yeah, I think really the next thing to look at is, you know, I'm sure we're all pretty familiar with all R squared by now. R squared is, you know, a number in between 0 and 1, and basically whatever that whatever that decimal is explains how much of the variation in the relationship is explained. Any questions on R squared? All right. So yeah, and then this was that whole like hardcore definition of R squared, which I don't think we're going to get tested on that. Mostly just understand that it is a number between 0 and 1, and it explains the amount of variation.
And I have a question on that.
Okay.
I think, do you think he'll, like in the list of options, maybe have it expressed in a percentage? Like, you know, when he asks like how much of y is being explained by x, and then we look at the regression tables, R squared, but do you think like the choices might be in percentages?
It could be. If it's worded
Yeah.
that way, then that would totally make sense, and I would feel that that would be correct.
Okay.
So you would
Yeah.
see like 0.89 on the regression table, but then on the answer sheet, it would say 89%.
89%. Yeah. Okay. Got it. Thank you.
All right. Yeah, if that's it for then, I'm just gonna go ahead and end this video real quick. And then we'll start a new one to knock out these last two, and hopefully we will be done.